Very good. Welcome back to the second part of this lecture. What I want to discuss now is the next stage in the development of Carnot's principle, which comes about as a result of Kelvin coming up with a decent notion of temperature. And so how did he do it? So let me bring out my screen and we can discuss it as follows. Uh, this idea here was discussing the efficiency of an ideal reversible engine. So the idea was that if you have an engine like this, let's just review this quickly. You have an engine from something that's hot to another reservoir that's cold. You have heat Q1 here and heat Q2 being discharged to the low reservoir. The amount of heat that comes out is the difference between the two. Now notice that these T's that appear here, this is just hot, this is cold. What this number is essentially irrelevant. You could use a mercury thermometer, or you could use an ideal gas thermometer, or you could use the resistance of a piece of wire when you send a current through it. All these numbers depend. Well, they not only depend on the substance, the thermometric substance that you're using, but they also depend on how you calibrate your scales. And the calibration of scales is completely arbitrary. You could do it linearly with one thermometric substance, but that does not mean it's going to be linear in another. If you use a gas of photons in an oven, black body radiation, the calibration is going to be not necessarily the same as if you use an ideal gas. What calibration do you use? That's the question we're trying to answer. So the way Kelvin decided to think was, we have this definition and we know that the definition for efficiency, which is W divided by Q1, the stuff you get out of the engine divided by the stuff you had to pay for. And so how do we analyze this concept a little bit more? Well, he said, consider the following. Imagine that you have two of these engines in series. So we have one engine here and this engine operates, let me see, from T1 to T2, and this is engine A. And then you have the T2 being used as the high temperature reservoir for yet another engine that operates between T2 and T3. So the idea is heat is being supplied there and some heat is being discharged here, and there is a certain amount of work, let's call it WA, the amount of work produced by engine A, which is Q1 minus Q2. And then the same Q2 from T2 down, here you have Q3, and this produces amount of work WB, which is Q3 minus Q1. Now, why is it interesting to think about such an object? Well, this is an engine, this is an engine, but this whole thing is an engine. It absorbs heat Q1, releases heat Q3, and produces work in the process. So one of the things that we can write here immediately is that, I don't know if I'm going to have space here, but we can write the efficiency of engine A is going to be given by WA over Q1. The efficiency of engine B is going to be WB divided by Q2. And there is also the efficiency of the combined machine, which is going to be the amount of work produced by the whole thing, WA plus WB, divided by Q1. So one of the interesting features we see immediately from here is that, let me see, maybe I should go to the next page. EC is WA, the work from engine A, the work from engine B, divided by the total amount of heat coming from the top. This we can definitely write as WA divided by Q1 plus WB divided by Q1. If we divide this by Q2 and put Q2 there, we can write EC is EA plus EB. Q2 and Q1. Let me see. I need to write an expression for Q2. Yes, I have an expression for Q2. Okay, let me see. What is it that I wanted to do here? Q2 is going to be Q1 minus W. It's from here. Let me see where I have it. Q2 WA from here. Q2 is equal to Q1 minus WA. Very good. So I'm going to go back. Come on. Q2 is Q1 minus WA, so that I have this expression EC is EA plus EB. Q1 divided by Q1, that's a 1, minus WA divided by Q1, that's EA. So here we have an expression for the efficiency of the combined machine, of the composite machines, in terms of two of the parts. Very good. Notice that the efficiency is always going to be something that's positive. You extract positive work, you transform some heat Q1, this part of it, into heat. If it were not, if some of these things, efficiencies are not positive, then you can really construct perpetual motion machines. Think about it a little bit, you'll see. So the idea is that these efficiencies are going to be contained between 0 and 1. Somewhere in between. In fact, you're never going to have complete efficiency. You can have a machine that is awful, that works, but it's always going to be positive. So each one of these terms here is less than 1, and it's positive. Because it is less than 1, look at this here. This object here is positive. This is positive, and this is positive as well. So notice, because these are all positive, EC is bigger than EA. So one of the things that this is saying is that if you have an engine like this, and somehow you lower the temperature of the low temperature reservoir from T2 to T3, you increase the energy of the efficiency of the whole thing. That's what's being said here. In the same way, notice that this expression here, EA plus EB minus EA-EB, can also be rearranged as EB plus EA, 1 minus EB. For the same argument then, come on. Sometimes these tablets do things you don't want them to do. There we go. So what this means is that EC is bigger than EB, which means that you can increase efficiency. You can increase efficiency by increasing the hot temperature or lowering the bottom one. Okay, very nice. So now let's look at what this expression here says. What we have here is a function E, which is a function of temperatures, appears here, appears there, and maybe they differ from each other because they refer to different temperatures, but it is exactly the same functional. So what we have here is a functional equation for this function efficiency E. So we're going to solve it. The goal here is now to solve this functional equation. Do you notice that this is the second or third time that we're solving functional equations in this course? We had one functional equation for the sum rule, another one for the product rule, yet a third one now for the discussion of efficiencies of engines. So what we're going to do is we're going to take our equation, and I'm going to write it yet again here. EA plus EB, 1 minus EA. And I'm going to change variables. Very good. So I'm going to change variables. How do we change variables? I'm going to change variables to a new variable. X is equal to the log of 1 minus E. What this is the same this is the same as saying that E is 1 minus E to the X. Oh, okay. You can see now let me put A, and A. I don't want to confuse this E, which is just the 2.7172, whatever, right? With the efficiency. So we're going to use this new choice of variables, and so I'm going to write it. I'm going to write this equation in these new variables X. And what we have is on the left-hand side, 1 minus EXC equals 1 minus EXA plus 1 minus EXB. 1 minus 1 minus EXA. So these guys cancel out, these guys cancel out, and so what we have is EXC with a minus sign minus EXA with a minus sign. Here we have 1, and EXA plus EXA, and then we have EXA, EXB minus EXB plus EXA. Those two guys cancel out, and what we conclude is that XC, which is a function of T1 and T2, is equal to XA, which, I'm so sorry, this is important, X1 and T3. It's a sum of XA, which is a function of T1 and T2, plus XB, which is a function of T2 and T3. Very good. So this is the equation we have to solve. How do you solve? So all we have done here is transform this functional equation in the e's into a functional equation into the corresponding x's. How do you solve this equation? Well, one of the things you can see is that the left-hand side here does not depend on T2. So if I were to take a derivative, this is the way you always solve differential functional equations. You take derivatives and transform them into differential equations. So take a derivative of this guy with respect to T2 and you get a 0 there. So differentiate with respect to T2. So on the left you get a 0. On the right you get xa t1 t2 plus dxb dt2, and that is a function of t2 t3. Let me rewrite them, get this guy onto the other side, and so I'm going to rewrite it as follows: dt2 xa t1 t2 equals minus dxb dt2 xb, which is a function of t2 and t3. Now, this equation is interesting here because this equation here depends on t1 and t2. This one here on t2 and t3. So the conclusion is that, well, look, there is no t3 here, right? No t3 here. Therefore, if this is to be equal, there is no t3 here either. This guy does not depend on t3. Now here you do not see a T1. So if you want to preserve the equality, there can't be a T1 on the left-hand side either. So this only depends on T2, that only depends on T2. So what this means is that whatever these functions are, this is only a function of T2. Now we integrate. And we integrate here on the left-hand side. You have this object here. On the right-hand side, what you're going to have is, how did I write this? Some function of T1 plus a function of T2. So the way this would work is that if you take a derivative with respect to T2, this guy here is killed, and this guy gives you the little g. So all of this to say that whatever this function was, is that it is a sum. This being a sum, where the first piece is just an integration constant for this partial differential equation, allows you to say, when I take the derivative with respect to T2, you cancel out the first piece. Okay, good. We're making progress here. Now, differential equations have boundary conditions. The boundary condition is that the efficiency of an engine operating between two temperatures has to vanish when the two temperatures are the same, right? Imagine what would happen if this. So you see, this is the upper temperature, but this is the lower one. If you just operate with the upper reservoir, the one you extract heat, the one you discharge heat, it's the same thing. That's the perpetual motion machine of the second kind that we have been discussing earlier. So the efficiency of such a machine has to be 0. Otherwise, you violate Carnot's postulate. So the boundary condition then is that if I were to put T1 here, which amounts to saying T1 here, this, okay, if I were to go back here, if I put the initial condition being that E is 0, 1 minus 0 is 1, the log of 1 is 0, so x equals 0. So let me go back to this. This is the same as x t1 being 0. So let me see, is that correct? Yes, it's 0. So I go back here, and if I put this equal to 0, that means that those two terms have to cancel each other out. So let me do that. So this boundary condition implies that x t1 t2 has to be given by a function of t1 minus the same function of t2. Substitute back into E the efficiency, and our expression for the efficiency is given here. What we get is 1 minus Ex, which is a difference of those two f's. So this is going to be 1 minus E to the ft1 minus ft2, which we can write as 1 minus E to the big F, let's call that little f, and E to the minus big F, that's going to be 1 over little f. We're done. Now, remember that I had said that, let's go back to where we were doing that. Here we were saying when you can increase the efficiency by increasing the temperature of the high reservoir and lowering the lower one, right? So what that means when you go to an expression like this is that you increase the efficiency by increasing T1, and that means you have to let me see, you increase T1, you want this guy bigger, so that means that this is a monotonic decreasing function, and the other way around, if you make T2 smaller, this guy has to increase, so that well, if you increase this guy here, because this is a minus, you make this whole thing smaller, and so the whole thing goes. So what that means is that F is monotonic decreasing. Decrease has a, that's bad. That's with an S, right? There, that's much better. So now what is it we want to do with these temperatures? If you have temperatures, what you want of temperatures is that if T1 is hotter than T2 and T2 is hotter than T3, then T1 is hotter than T3. All of these temperatures are doing, all of these quantities that purport to measure a degree of hotness are doing is just ranking the systems according to the degree of hotness, right? So what we propose to do, given that these functions here are monotonic decreasing, is instead of ranking them according to T1, T2, T3, you rank them according to F. So what we propose is to regraduate the temperature scale by F. And the way we do it is just invent a new scale, which is just a constant multiplied by this F, clearly the constant here, well, no, it's just a constant. It's something let's come to it in a second. So that then, when you regraduate in this way, the efficiency, which is a function of this regraduated variable, is just going to be 1 minus, did I get these things backward? Yes, I think I got these things backward here. We should check. So that this is just going to be T2 divided by T1. Oh, sorry about that. I should be a little bit more careful here. EF T1 is G FT1. I should have defined this differently. I should have. Let me see if I can get this straight quickly. FT1, FT2, so that X. Well, my notes tell me that the correct number here is T2, and this is T1, and okay, e to the minus f. I was regraduating differently. Of course, it makes no difference, right? But the jump from up here to down there is given by e to the minus f. This is the way this is defined. It's one of those problems. It's difficult to find a mistake when you didn't make one. Actually, this is all very consistent. This is the way to do it. If I had kept the other way I was doing it with e to the f being f, then I ought to define capital T as C divided by F, and then I would get exactly the same answer. Very good. Now that I got that confusion out of the way, this is the efficiency. Now notice, these temperatures are not any better than the old ones. They're more convenient, that's all. The same ranking of hotness is given by the old lowercase t as by the uppercase t. And so what this means is that now we have a much more, much simpler, much more convenient temporal temperature dependence of the efficiencies if you define this new scale. The constant C that we have here, that's just a matter of the choice of units. You could use units that are very arbitrary, like you choose freezing point of water as being C and the boiling point of water as being 100, and that defines your degrees, right? And but you could choose anything you want. You could choose degrees that resemble Fahrenheit. That would be fine. Obviously, it cancels here, right? Any constant of proportionality cancels there. So what this means is that as your thermometer, you can either use an ideal gas or you can use something else like a gas of photons or whatever. But the thermometer that is very particularly clever to use is the efficiency of a Carnot engine, right? The efficiency of, sorry, Carnot engine, of a reversible engine. Since these engines do not exist, it's clear that this is an idealization. Very good. Let me see, how are we doing here? I want to point out one more thing. So one last thing. Carnot's principle, let's just write it out one more time. What Carnot's principle says, any engine E prime is less efficient than the reversible engine, and the condition is that this guy operates between two temperatures, and this guy operates between the same two temperatures. How do we write that down? Okay, we write it like this. The efficiency of the arbitrary engine is going to be given by, and here the two temperatures. By the way, it's not a good idea. Okay, no, I did something wrong here. What did I do wrong when I even wrote that expression? I see the efficiency of the arbitrary engine depends on T1 and T2. No, 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 no. The efficiency of an arbitrary engine will depend on all sorts of things, whether it is made of one substance or another, whether the material that makes the walls of the container are steel or ceramics or whatever. This guy depends on anything. However, the efficiency is always defined as the amount of work divided by Q1. And this is going to be less or equal than the efficiency of the reversible engine. There, that one. And the efficiency of this guy is 1 minus the low over the high. So here we're going to take one further step and say the efficiency is the work divided by Q1, which is equal to 1 minus Q2 over Q1. And this is less or equal than 1 minus T2 over T1. So now that we look at this expression here, we can cancel the ones and we can divide by T2, divide by multiply by Q1. And so what we're going to get here is Q1 divided by T1 minus Q2 divided by T2. This is going to be negative. So far, you see, I haven't written anything. It's just, this is another way of writing Carnot's principle. E prime is less than ER, but if I massage it a little bit, I can write this expression. Now, instead of writing the expression in terms of Q for the engine, so here's your engine, and this guy absorbs Q1 and releases Q2. It is convenient to write this in terms of heat flowing into the engine, so that this guy, we're going to write it as positive heat Q. The little Q's are positive when this is going in and that one is going out. The big Q's are positive when they're going in. So negative when they're going out. So Q1 is positive and this Q2 is negative, so that with that minus sign, it gives you the positive one. When we write it like this, the expression of Carnot's principle is Q1 over T1 plus Q2 over T2. This is Q1, Q2. This is negative. Now this is just for an engine that has two reservoirs. You can also write this for an engine that has many reservoirs. Now clearly this is going to be even less efficient than something than an engine like this, right? But nothing prevents you from rewriting Carnot's principle now for a cycle of engines. Imagine that you have an engine that receives Q1 from one temperature, Q2 from a different temperature, Q3 from a different temperature, and then here heat going out, the lower ones, but still this is negative heat Q4 from yet another temperature, negative heat Q5 from yet another temperature. You can have a much more complicated object, and under those circumstances, what you have is that the sum of all of these heats coming in at the temperature of the various reservoirs, this is going to be negative. So this is a generalization of Carnot's principle. And the way you might actually think about this is as follows. If you have just two reservoirs, and this is T1 and this is T2, and these are the isotherms, and then you have the adiabats, the cycle for the engine would be something like this, right? So this is a Carnot cycle. You can imagine now what happens when you have, so this, what is this? For an ideal gas, the variables would be PV. What happens if you have a more complicated cycle like that? Well, nothing prevents you from drawing the adiabats like my picture here is kind of messy. Let me see if I can do this. Something like that. And then you say, look, this guy here corresponds to one of these Carnot cycles. This guy there corresponds to another one of those. This guy here, and these are these little choppy things up here, there, those are the isotherms, right? And so each one of these, any arbitrary cycle can sort of be expressed as many Carnot cycles of this type. And so this is what would lead us to an expression that in the continuum you can imagine having heat being absorbed at different temperatures, and for a generic engine this is necessarily going to be equal to 0. For a reversible engine, then this is all going to be, that's when you obtain the equality. What we're going to do next time is explore the consequences of expressions of this type. Notice what we did here. We were expressing Carnot cycle in terms of efficiencies. That's this inequality here. When we do that, we manage to write an expression in which you have an engine that operates just between two temperatures. Now, of course, that's the most efficient way to do it, but you could consider engines that operate that are less efficient and are even worse than this, right? And so for those engines in which you get heat from many different reservoirs and throw heat out at many different temperatures, you obtain an expression like that. And in the continuum limit, you could imagine an engine that operates in some arbitrary cycle like that. And for that, it would be something like this integral that is less than 0. Do you see the expression for entropy starting to show up there? That's what we're going to be discussing next time. The person who wrote this expression here naturally was Kelvin. He also generalized it to more complicated cycles like that. And it took yet another 10 years or so. Let me see this. I believe this was like 1865 when Clausius realized that by writing these expressions in the continuum, he could actually make these calculations go one step further and do something useful. And what he did that was useful was to realize that these considerations are all very very fine, very nice, but they refer to processes that go in a cycle. Wouldn't it be interesting to have ideas like the ones that we are discussing here that allow you to discuss processes that are not cyclic? Most processes out there in the world are not cyclic. It is a feature of engines that we want them to be cyclic because we want them to operate over and over and over again. But in general, processes are not cyclic. So this is what Clausius realized. This generalization of Carnot's principle is what's going to be useful to describe non-cyclic processes. That's for next time. Thank you.